все вообще выглядит.
Сейчас хорошо.
Хорошо.
So, okay. So I talked about SL2. So SL2 is a three-dimensional Lie algebra complex, and it has a basis of H, E, and F with the following commutation relations. So it is the most simple Lie algebra, non-commutative, I think, ever. So, and then we want to consider a representation of SL2. So I want to consider a Fermat module. It is, generally speaking, an infinite dimensional representation. We'll denote it V lambda. So how we construct it? We construct it in the following fashion. So consider a highest weight vector. We'll call it V. So with the following properties. So the first property is that H acts on this vector by scalar, lambda. E annihilates V. And I think that's all. So then V lambda is span of V, FV, and so the module is just generated by F. So the elements of V lambda are the following sums. So here I allow infinite sums, so it is something like completion of Fermat module, but it's not very important. So alpha I, F in the power I, acting on V. So here alpha E are some complex numbers. So yeah, so this is the form of vectors in Fermat module. So now I want to find such a vector, which is called Whittaker vector. Which I define by the following equation. I will denote it W with index mu, and it has a property that E acts on Whittaker vector by a scalar mu. So it is something like a coherent state. So the element E acts by scalar. And one may ask if such vector exists. And the answer is yes, and we can compute it. So let me compute it maybe. So we know how it looks like. It is just an infinite sum. I act on a Whittaker vector. So then I use, so I have here E and F in some power. So to move E forward, I use these commutation relations and obtain something like sum alpha I sum k from 0 to E minus 1 lambda minus 2. Okay. So again, since I can't see anyone, so please, can anyone still hear me? Or if you have some question, if you do not
Hear
have
you, yes, everything
Okay.
is clear.
Okay,
Up to now.
it's great. Now I understand that I have a connection to the internet. So we want to perform a summation of arithmetic progression. It will be quite difficult. Lambda plus lambda minus 2e minus 1.
Sorry. I would say lambda I.
So, okay, let me, it is a very simple task to fail in this summation for me. So I want to sum what? Lambda plus lambda minus 2 plus lambda minus 4, then lambda minus 2 I.
Maybe it's simpler to take first sum, lambda.
Yeah.
It will be multiplied by I. The second sum gives I times I minus 1.
Yes, I lambda. We have I times lambda, yeah, and then minus, very difficult, I minus
I times I minus 1.
I think it is correct. So yeah, thank you. It is very difficult to do such calculations.
Extremely difficult calculation. Yes, I agree.
Yes, I think it is correct. For I, so here, I and lambda minus e plus 1. Yeah. So, and this guy should be equal to mu and Whittaker vector. Great. So this means that e lambda minus e plus 1 on alpha I is equal mu alpha I minus 1. Yeah. So we have a simple recurrent formula. So alpha I is equal to
Misha, probably the sum should be taken from 1 to infinity, not from 0.
From 1.
Because otherwise,
if I equals 0, you have E
Yeah.
acting on vacuum, and otherwise you have F
Yes.
to negative power. Yes.
Yes, you're right. So this term in 0, it will just be 0, and it is okay. So alpha I mu I lambda. And from here we see that we can impose such a condition that alpha 0 is equal to 1, then alpha I is in power e, e factorial, and okay, so lambda, then lambda minus 1, and 2 lambda plus 1. So I hope this is correct. Yes. So thus we have found an explicit formula for Whittaker vector. Great. So if there are any questions, please ask. If I missed something, please state. Okay. Well,
Миша, можешь еще раз показать этот вектор, который мы нашли? У него форму. Да,
this is
спасибо.
a
Спасибо.
formula. Then I want to define a Whittaker function. And for this, I need some help. Not to confuse with signs. All right, so W of phi is equal to, okay, then let me go in this way. So what is written here? Here we have a Whittaker vector, and here we have dual Whittaker vector with a different subscript mu prime, and dual Whittaker vector is defined just as the ordinary one. We impose the condition that not E acts, but F acts as scalar. Okay.
Okay, except that you write subscript in different positions.
Yes, it is. I always want to write it on the right, but then in this formula, this will be maybe not very convenient. So, okay. Yeah. Mu prime is in C. And then we want to work a bit with this function. And I want to prove that it satisfies certain differential equation. So what I need for this, I need a quadratic Casimir function of SL2.
Mikhail, sorry, my very stupid question. I
Yeah.
hope E in the formula is not E, but exponent. Yes.
E is exponent, yes.
Okay.
E is exponent. Oh, wait. Yes. E. Oh, okay. So I will maybe I will write it in the following way. Yes, of course, E is exponent. So we introduce quadratic Casimir. lies in universal enveloping of SL2, and it commutes with everyone. Thus, in irreducible representation, such as Verma module, for almost all lambdas, it acts as scalar. And C acts as a scalar on V lambda. And we can simply compute on so E annihilates V. Then EF, we can move E forward and make it FE plus this is equal to FE plus H. And then everything annihilates except for this guy and plus H. Okay, so then I write lambda plus 2 divided by 2 is equal to first Whittaker vector, then exponent phi, ph. Insert Casimir function. Consider such matrix element. Okay. Then I consider, I will write here in this way since it is shorter, right? Plus 2FE. Yes. All right, so I divide this expression into parts. The first part is with h's. So I want to work with this part. So firstly, we can see that E acts on Whittaker vector, and this gives us mu. Let me say that this expression equals to something like A. So A plus 2 dual Whittaker vector H F and mu. So now I want to move F to the left using the commutation relations between F and H, and this is very difficult. So I will see the correct formula. So the correct formula is H equals to f. I hope it is correct. Then I can move f to the left. It's equal to f acting on the dual Whittaker vector gives us mu prime. Great. So I write everything explicitly now. So then this guy is a Whittaker vector itself, and this is a differentiation of Whittaker vector, and we can write it in the following way. So the first is 1/2 of second derivative plus derivative with respect to phi. And thus we see that Whittaker vector satisfies the following differential equation. It is an eigenfunction of this operator with eigenvalue lambda plus 2 divided by 2. So this operator can be brought to the form of open Toda chain, and so the potential is exactly as in the open Toda chain. So I will call this open Toda chain. I don't want to spend much time doing it. So Igor did it, but I don't want to. So please, if there are any questions, please ask. And if you can still hear me, please say something like it is very bad, everything is very bad, everything is very good, something.
Все хорошо.
Отлично.
Мне кажется, я понимаю, но может это обманчиво.
No, everything is quite simple. And again, my talk is very simple, I think. So
what was your goal? Just
yes,
to derive this differential equation?
No, this differential equation
for Q case.
So this was Yegor's goal. My goal is to perform such calculations for quantum group for quantum SL2.
Okay, I see.
So it is it's not difficult. It is just some work with quantum SL2, and as far as I remember, we almost never talked about quantum groups. So I thought that it will be maybe helpful for someone, maybe not. So now I will move forward to the Q case. So Q vector. So before moving forward, I must say something about higher rank cases, for example, SL3, SL4, and other Lie algebras. So as far as I remember, in the classical case, everything is more or less the same. We impose the same conditions, like E will have more E's. So this E acts on Whittaker vector as some scalar, and this is just some work to prove that such a Whittaker vector exists, and then to derive a differential equation on it. So in the Q case, SL3, SL4 is more difficult than SL2, but still SL2 is a good example where we can see the differences, we can understand the nature of such Whittaker vector, I would say. So first of all, I will start with definition of SL2, quantum SL2. So if there is someone who doesn't know what it is, quantum SL2, so please ask any questions. I do not know how many people are listening to me, so I don't know. I know nothing now. So I denote quantum SL2 in this way. So it is a quantized universal enveloping algebra. So in the following way, it is a
Ну, слышно хорошо, продолжайте, все нормально.
Is associative algebra. Generated by 3 or 4 elements, as you like. Generated by K plus minus 1, E, and F. With relations K on K minus 1 is 1. Commutation relation with K and E.
I guess you should change the order in some
Yes,
part.
thank you. Okay, so these are the only relations. So then if we, so why is it called quantum SL2? Because if we set K equal to exponent of epsilon h and then send epsilon to 0, then we will find commutation relations between H, E, and F just the same as in the SL2 case. And then, of course, we should somehow do something with Q. Q will be something like this, I think. So, and I'm sorry, please wait a minute. I will So I needed some water. It's not very simple to talk so much. So this is the definition of quantum SL2. And this is all that we need for quantum Whittaker vector. So we introduce a Fermat module. V lambda. Again, it is generated by some highest weight vector V with the following properties: that K acts on V as Q in power lambda, and E annihilates V. Great. So then V lambda is generated by F. So the general vector in Fermat module has the form of infinite sum. And then we search for a q-Whittaker vector, which is defined just as in the non-quantum case. E on Whittaker vector with subscript mu is equal to mu. So this is the definition of Whittaker vector. So here it is very important that we consider SL2, and SL2 is very simple. Because of this, the definition of Whittaker vector is just the same as in the non-quantum case. For SL3, SL4, and other quantum groups, will have a different definition, because we'll have Q-set relations. They are more difficult. So, and in SL3, SL4, and others, it will be more difficult. The definition will change, but in SL2, it is just the same as in non-quantum case. So it is a very good example to perform some calculations. Okay, then we try to find Whittaker vector.
But in classical case, we don't have to change something. Just want to all E alpha access some mu alphas.
Yes, yes. In the classical case, EI on Whittaker vector is mu I Whittaker vector. And in quantum case, this will be something like, I think this sign, KI, EI, something like this. Again, this is due to quantum set relations. So we can't just write that EI acting on Whittaker vector is equal to mu I. But in the quantum SL2, we do not have Q-set relations, so everything is okay.
What do you mean we cannot write? Suppose I wrote exactly like in classical case. What will be the consequence?
There will be no such vectors.
So such vector does not exist. Yeah.
Yes. Yes. This definition will not be compatible with Q-set relations.
Wait a minute. There is one Whittaker vector in higher rank algebras, because actually you write for Whittaker vector subscript mu. In classical case, there is one vector or mu I.
For if we have chosen mu's, I think more or less yes, up to some scalar.
Whittaker vector is only one for each EI, but with different mu I.
You should fix a lot of mu's.
Yes,
Mu
so
now be a vector.
yes, mu is now a vector.
Okay, so and EI acting on Whittaker vector with mu. Mu is multi-index in this case.
What?
Mu is multi-index. Well,
No,
right.
Here, yes. Or I can write.
And with Whittaker vector is single vector.
What do you mean by single?
So if you fix this vector mu, so the vector is only one. Well, up to
No,
scaling.
I think yes. If I'm not correct, then sorry.
Okay, and in quantum case, you say that if you require the same condition,
There will be
vector
none.
doesn't exist.
Yes, this definition is not compatible with the C relations.
I see. Okay, thank you.
Thank you for where we are. We are searching for with a q-Whittaker vector. So I write it in the general form, and we perform all the calculations that we did in SL2. They are more or less the same, actually. So the story is not difficult. So alpha I, fi on the highest rate vector. I act by E. And perform some arithmetics. For I, E, I. Now, we want to move E to the right. We use this relation to do it. And thus we will get it will be very difficult from 0 to I minus 1.
Can I guess we should change all factorials to q-factorial?
Maybe, but Ivan, you are too smart. Let me do some calculations. So this k, this k minus 1. M. Yeah. So I'm sorry for all my mistakes. I performed all the calculations before the lecture, but I'm now in such a position that I cannot look at them at all. Divided by q, it's q minus 1. Fi minus 1.
And again, the lower limit of the sum is 1, not 0. The sum with I from 1.
It is very Yes, it is a mistake that I cannot remember. Yeah, so now we want to perform a summation of geometric progression. We will see if I can do it. Mm, 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 mm. Um, oh, I hope it is correct. Now we can simplify. Let me see how we can simplify. Mhm. Mm, mhm. Right, let me do it in the following sense. Mm,
And plus I, probably.
Plus
Lambda plus 2 plus I will be better.
yeah, yes, I know. No, I want to multiply this by qi. Thus, I want to, and here we'll have qi minus q minus I. Oh, this is very difficult, sorry. Q minus q minus 1. Is it good, Vanya? So I just want this to be a q number.
Okay.
Okay, great. So so this is, I will denote this by EQ, Q number. This is just a definition. I minus 1. this is EQ minus Q minus lambda minus 3.
Again, the I minus 1 times V.
Yes. I hope that all the calculations are correct. This is again a Q number, yes? I think yes. Yeah, everything is good. Now, we wanted this to be equal to mu Whittaker vector. This gives us a recurrent relation for alpha i's. I and then we impose the condition that alpha 0 is 1, and then alpha I is equal to mu in power I. Q factorial. Maybe okay. So this is Q factorial. This is just a product of E, Q, E minus 1 Q, and so on. This and this part. So, and this is the explicit formula for the coefficients of the Whittaker vector and thus for Whittaker vector itself. Okay, are there any questions? Maybe there are some mistakes. I'm not sure that I performed all the calculations correct. Vanya, is it okay? Or Nikita Andreevich?
Okay.
Seems to be okay, yes.
Okay, great.
But I
2
think
is
that you
for
don't
C
need
check.
this.
What?
2 is for C check. Yes.
What? I don't
Lambda
remember.
plus 2.
Lambda plus 2.
3 instead of 1. Just because of it is a quantum group and you need to shift something.
So the question
Can
is
you
about
compare this
yes.
relation? In
Yes.
classical case, you have just 1.
Yes.
And now it's dual Coxton number, or what?
Okay, let me copy paste and then we will compare. Okay. Okay, I copy and then I will paste so we can. Okay, enumerators are the same. This is very good. So here we have ordinary factorial. Here we have Q factorial, and here why where we start from lambda plus 2, and here we start from lambda. Yes, I think, Vanya, this is somehow connected to something like Coxeter number, but I'm not sure to Coxeter number or dual Coxeter number. Since it is SL2, it is quite difficult to say if it is a dual Coxeter number or Coxeter number. So,
and could you show once more definition of vector V in quantum case?
V, which is highest weight, yes?
Highest weight, yes.
Yes.
So it's q to the lambda.
Yeah.
Oh, then it's a bit strange.
Yes, I agree. So maybe there is something wrong. Let me see a bit. Okay.
So this 2 appears after commutation relation.
Yes. These two, of course, appear after commutation relations, but in classical SL2, let me think a bit.
Wait, can we check, for example, I equals 1?
I equals 1. Wait, you want to check?
Well, you commute, no, a bit higher. You commute E with F to the I.
Yes.
Yes. For I equals 1, you should obtain what?
Q lambda minus Q minus lambda, yes?
Okay. And instead, you obtain in your formula Q to the lambda plus 2.
Yes. Yes.
So I guess the reason is here hidden. You
yes,
shift
so,
M
yes.
by 1,
yes.
but you should not shift. If you don't shift, you just you have no shift lambda by 2.
Yes, you're completely correct. Much thanks to Nikita Andreevich and Vanya. So I think that here, everything is correct except for these guys. So here we'll have plus 1, here minus 1. Plus 3 plus 1. One. And now everything is perfect. And now the formulas are completely the same, except for the fact that we changed all the numbers to Q numbers. I think that now we're all happy. I'm very happy. Very much thanks. Okay. So I delete guys. So now we want to introduce a q-Whittaker function. Which is defined by the following formula. power minus phi. So again, the dual Whittaker vector is defined by formulas that f x by m prime. And here, to avoid any problems, we may say that here phi belongs to integer numbers. I think that it is okay to think about phi not as an integer, but to avoid any questions, any problems, we may think that phi is an integer. So then we can ask if there is any differential equation for this function or difference equation. Actually, in the quantum case, we will have a difference equation for the q-Whittaker function. And to obtain it, I want to introduce a Casimir function for the quantum SL2. So C, which is equal to, let me see. K plus minus 1, K minus 1 divided by K minus 1 squared. So it is a quite simple task to prove that C commutes with everyone. As in an irreducible representation, it is again a scalar function. We can compute how it acts on the highest weight vector. And this acts by 0, and so this is no. It's not a K number. Okay, this is the formula. Now we want to insert the Casimir function inside the Whittaker function here, and
And
now
before all these
yes.
calculations, one question. Is it important for you the value of Q? Is it less than 1, or maybe it can be root of unity in your calculations? Yes. Is it important?
I think that it is not very important. What is important for me is that the Verma module is irreducible. So I think that it is true for almost all lambdas. So again, if we look in the formula of for coefficients for Whittaker vector, if lambda is an integer, yes, so we'll have some problem. We will divide by 0. So we know why, because if lambda is 0, then the Verma module will be reducible. It will have a finite dimensional quotient. So I very much assume that Verma module is irreducible. But to avoid any problems, I can say that Q is not a root of unity. About Q is less than 1, or so. Let me think. We may have some problems with the divergence. Yes, maybe.
Maybe yes. Wow.
So let me say that I don't want to talk about it. So I consider just formal power series. So it is an interesting question. I should think about it, but now I want just to say that,
Maybe in your case it's not crucial.
But I think it is important if we would like to think about q-Whittaker function as a real function, not just some formal expression. But for my calculations, it is not really important.
Okay, let's see.
Okay, so everything will be just as in the SL2 case, just with some differences with commutation relations. So, okay. So I write explicitly the Casimir function, the Casimir element f e plus q k q minus 1 k minus 1 . So again, I want to divide the Casimir into 2 parts. So this part is not very difficult. So, and this part, with this part we'll work knowing that this guy is a Whittaker vector and this guy is a dual Whittaker vector. So E will act on Whittaker vector and give us mu. So let me write. So yes. Now I want to move F to the left. And, to do it, I use commutation relations between K and F, and then I will obtain, let me see, I rewrite the first expression. When I move F to the left, it will act on the dual Whittaker vector and we will obtain mu prime. And because of these manipulations, the argument of phi, I mean K minus phi, will become minus phi I want k minus phi f is equal to q. Yes. So if phi is -1, then it is good. Yes. Phi. Right. So, and this is the initial Whittaker function. Very good. Now I want to work with this part. Working with this part is quite simple. So here we have k, here we have k minus 1, and this can be performed by shifting the argument. So the first part, to obtain the first part, we shift by phi by -1. So I will write in the following way. Q tau minus 1 plus tau plus phi on Whittaker. So and t acts on function of phi as the following way: it shifts phi by 1. Thus, we calculated that with a q-Whittaker function satisfies the following difference equation. Or better to say, it is an eigenfunction of a difference operator. So function, the eigenvalue is lambda plus 1 plus q minus lambda minus 1. So to simplify, we can multiply by q minus 1 squared to make it more good looking. Okay, and so this difference operator can be identified with what is called the q-Toda chain or relativistic Toda chain. I guess the name q-Toda chain is due to Etingov, and relativistic Toda chain is due to Rusnars. It is done by some change of variables. I don't want to do it. It's not very interesting. But we should think about this operator as a relativistic quantum Toda, open Toda chain Hamiltonian. So using quantum SL2, we have constructed some eigenfunctions for it with certain eigenvalues. And actually, this is all that I wanted to say today. So if you have any questions, please ask. If you want me to continue the talk about maybe affine algebras, maybe higher rank in quantum case, higher rank in classical case, I think I can do it. If you are interested, of course. If you are not, please say. I will be very happy not to talk on the next Tuesday. So please, any comments, questions?
What is the relation between Whittaker vector and Whittaker function?
The relation is the definition of Whittaker function. Whittaker, actually, to construct the Whittaker function, we need two Whittaker vectors.
Yes, but okay, maybe I can formulate in slightly different manner.
Yes.
So can you show expression for the coefficients of Whittaker vector? Yes.
Yes.
Okay, now suppose we construct a function alpha I times phi to the I and the sum over all I. So we obtain function of phi.
I missed something. Let me write something. We want a function.
So originally Whittaker vector was alpha I times f to the power I. Acting on vector v. It was f capital.
In the quantum case, yes. This was a Whittaker vector.
Yes, I to the minus 1. Yes, simply I. Okay, now we erase v and replace f by some variable, complex variable x. We obtain function of x.
So erase v, yes.
Yes.
And
instead of f, we write down some x number x. So we obtain function of x.
Yes. Okay. And okay. I do not think that it is somehow connected really with the Whittaker function. This one, but of course we can ask, what is it? Yes.
Yeah.
So firstly, we can ask, is it really a function? Yes. And it is a question about q. Yes. I think.
Well, it's a question of convergence of the series.
Yes.
Suppose it is convergent, then we obtain some function.
Yeah. So I do not know really anything about such expressions. Maybe they have. So they do not look very complicated, these coefficients.
Yeah.
But I don't know. So.
But definitely it is not solution of difference equation. If we replace x with phi, for example.
I think no.
At least because difference equation depends on two parameters, mu and mu prime, and here we have only one.
It's not really that difference equation depend on mu and mu prime. They depend on mu
times mu prime.
Yes. So it's not really important that we take Whittaker vector here with mu, dual with mu prime. It's just.
Okay, so maybe this is solution of difference equation.
This function, maybe for some, but I do not think that. Okay, so we can try to just compute this one, yes? Just write expression for this, expression for this. Then what we will have? We will have to compute following matrix elements.
Yeah, it will be maybe not very easy.
So here E to some power K minus V, here Fi. I do not think that after all such calculations, this will account just for replacing.
Okay, yeah, I agree. Well, maybe we should maybe do something with this function of x.
But now I remember there are some expressions for Whittaker functions in the integral form. So it is what I think I know this from works of Gerasimov, Ablezin, Lebedev, I think.
Lebedev, I see.
So they are not just some like very easy functions, but we have some expressions for them different from these like matrix elements type expressions.
Okay.
Okay, if there are no questions, so please state something if you would like to hear more about this topic, or if not, I would prefer if you would not like, but maybe somebody is very interested.
Maybe for higher ranks, but without maybe so explicit calculation.
One moment, let me. So I think that my screen is not very important now. I will stop sharing and let me try to.